Now we're going to talk about how to perform multiplication of matrices. So let's start with this. Let's say A is an n by p matrix and B is a p by q matrix. All right? So if we're performing A times B, what we have here is an n by p times a p by q matrix. What's significant here is this. The number of columns of A must equal the number of rows of B. Okay? I'm not saying here that n has to be different than p. I'm not saying that p has to be different than q. What I am claiming, though, is that the number of columns, that's this p right here, in A, must be equal to the number of rows, that's this p, in B. And then the result will be an n by q matrix, these values right here. Okay? So I find it's easier to teach multiplication by just doing an example. And it will also make it more clear why these dimensions have to be this way. So let's say that A is equal to 1, 2, 3, 4. Okay? And B is equal to 1, 0, minus 1, 2, 3, minus 2. All right? So if I want to perform A times B, I have this 1, 2, 3, 4 right here. And then I have 1, 0, minus 1, 2, 3, minus 2. So we know it will be what? So this is a 2 by 2 matrix. This is a 2 by 3. So the result should be 2 by 3. Right? This right here, 2 by 2, 2 by 3. And based on what I told you here, it's the outer dimensions. That's this number by this number. Okay? So how do we get the first number? What I'm going to do is I'm going to take this first row, turn it sideways, such that it matches up with the first column, and multiply the corresponding elements, and then produce the sum of those products. That's the reason why the number of values on this row has to equal the number of values in this column. Okay? So this first value here would be 1 times 1 plus 2 times 2. And we'll simplify this in a moment. Now, I'm going to take this first row of A, turn it sideways, and match it up with the second column of B. And that now will be the second column, or start the second column of A times B. So that's 1 times 0 plus 2 times 3. 1 times 2 times minus 1 minus 2. So the third column I do the same thing. 1 times minus 1 plus 2 times minus 2. And these three numbers, once I simplify this, that's what I'll have. These three numbers will form the first row of my answer. To get the second row, now I'm going to take this second row of A, turn it sideways, and match it up with each of the three columns of B, produce the products of the corresponding elements, produce the sums of those products, and that will give me three numbers at the bottom. So that then will be 3 times 1 plus 4 times 2. 3 times 0 plus 4 times 3. 3 times minus 1 plus 4 times minus 2. All right? So if I simplify, I have 1 and 4 is 5. 0 and 6 is 6. Minus 1 and minus 4 is minus 5. That's the first row. And then I have 3 and 8 is 11. 0 plus 12 is 12. Minus 3 and minus 8 is minus 11. There's the answer. Okay? So once again, how do we know how all this works out? Well, The answer has to have n rows because I'm taking each of the n rows of A and multiply it by the columns of B. So that produces n output rows. Okay? I took each row of A, multiplied by each of the Q columns of B, and stored it in one of the Q columns. That's why I got Q, or 3 here, columns of the output. And then once again, since we're saying, if we look at like the first row here, the first row of A is this, 1, 2. This first column of B happens to also be 1, 2. We see now why this P and this P have to be the same, right? I take this, turn it sideways, match them up, and multiply it. Okay? So that's matrix multiplication, and we'll do lots of that throughout the semester. So let's talk about the rules for real numbers and how they relate to matrices. Okay? So we know that for real numbers, right, we have commutativity, that is A times B is equal to B times A. For matrices, in general, AB does not equal BA. Okay? Why would that be? Well, there's several reasons. One is the shapes may not even allow it. Let's say I have this. Let's say, well, the previous example, we had A times B, so we had 2 by 2 times a 2 by 3, and that produced a 2 by 3. But if I try B times A, now I have 2 by 3 times a 2 by 2. These are different, so it's not even legal to do that. So it's not even possible to do that. Okay? What if I had this? What if we have that A is M by N and B is N by M? Okay? And let's say for this example that M does not equal N, so therefore they're not square. Well, AB will be equal to an M by N times an M by M matrix, which will be what? M by M. Right? If I do BA, then I have N times M by N, which is an N by N matrix. So both directions are legal. These match up, but since I said let's assume that M is not equal to N, then these shapes aren't the same. For example, this might have been 3 by 5 times 5 by 3. Well, going this way, we get a 3 by 3 matrix, but going the other way, we get a 5 by 5 matrix. So obviously can't be the same. Okay? So what about if both matrices are square and they have the same number of rows and columns? That is, they're both, say, 3 by 3. Well, if A is 3 by 3 and B is 3 by 3, well, then both directions will produce a 3 by 3 matrix. So there are situations in which then you could get the same answer. There's also situations in which you don't. Okay, well, let's say we have this. A is equal to 1, 2, 3, 4, and B is equal to 1, 0, 0, 3. If I made this an identity matrix, then it would commute. Okay, but this is not an identity matrix. So AB is 1, 2, 3, 4. Sorry, it's a 3, 4. 1, 0, 0, 3. So 1 times 1 is 1, plus 0 is still 1. 1 times 0 is 0, plus 2 times 3 is 6. 3 times 1 is 3, plus 0 is 3. And 3 times 0 is 0. And 4 plus 4 times 3 is 12. So I get 1, 6, 3, 12 this way. If I go the other way, which is legal because I have the right shapes, now I get 1 and 0 is 1. Those are the same. Then I get 2 and 0 is 2. Those are already different right here, right? Let's continue just for the practice. 0 and 9 is 9. And then we get 0 and 12 is 12. So those are also the same. But these, the 3 and the 9, are different. And the 6 and the 2 are different. So the diagonal terms for this particular problem, don't assume that we can generalize, but for this particular problem, it worked out that the diagonal elements were the same, but the off-diagonal terms were not the same, demonstrating that you can't assume that AB will always be equal to BA for many reasons. All right? What other things do we know? Real numbers. If I have A times B times C, then because multiplication is a binary operation, which means you really only multiply two things at a time, this requires us to either multiply A times B first and then multiply by C, or we can multiply B times C first and then multiply by A. This is called associativity. So it's associative. That is, multiplication of real numbers is associative. What about for matrices? Well, it turns out it's also associative. If I have A, B, and C with dimensions, say n by m, m by p, p by q, right? So those are the same. Those are the same. Well, it turns out I can multiply AB together first, and then multiply by C on the right. Right? Remember, we can't do like I could do over here, where I could take the C here and move it over to here and still get the same answer, because that would be commuting. Okay, so this still requires a C be on the right in this case. So this would produce an N by P matrix. So I still have the right dimensions to produce the next product, and then you multiply by C. Or we can multiply B times C first, and then multiply by A on the right, since that's where it's at. So it is associative. Okay? Distributive property. A times B plus C is equal to AB plus AC. Well, that's true of matrices if you have the right shapes. All these are contingent upon the right shapes, otherwise nothing else matters, right? So A times B plus C is equal to AB plus AC, and B plus C, let's say times D to distinguish between this A, would be BD plus CD. So this would require in this case that B and C have the same shapes. So you might have something like this. A is M by N, B and C are N by P. Okay, so these match right here. Sorry, the N and the N here. And then D is P by Q, right? Because if I add B and C together, I just get another N by P matrix. So M by N times M by P gives me an M by P matrix. And then likewise, if I add B and C together, I get N by P, multiplied by B times Q, I get an N by Q matrix. So the distributive property holds. Okay? What else do we need to know about that? Multiplication by a scalar. So this isn't really about real numbers anymore. Now it's specific to matrices, but multiplication by a scalar. So whether I have something like this, let's say K times A plus B, where K is a scalar, this would be Ka plus Kb if we want to do it that way. We could have scalar C and K added together times matrix A. That would give me Ca plus Ka. And then also if we were to have something like this, C times K times A, that's equal to, we could do it C times K times A, or C times Ka. So how do I even do multiplication by scalar? Well, I simply just multiply the scalar by each element of the matrix. So here if I have, say, 3 times 1, 2, 3, 4, 5, 6. That's equal to 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12. 3 times 5 is 15. And 3 times 6 is 18. All right? Now, one of the things that distinguishes scalars from other things involved in matrices is the concept of commutativity here is not really an issue like it was for matrices, because you're not changing which terms interact. So even if I had something like this, to make the math easier, I might do something like this sometimes. Let's say I have 1, 2, 3, 4, and I might have, 10, 20, 30, 40. This isn't really going to be an example of how it helps. But what I could look at and say this right here is really just 10 times 1, 2, 3, 4, right? Based upon what I just showed you here. So I can actually factor that 10 out. So this right here really is just 10 times 1, 2, 3, 4. 1, 2, 3, 4. They'll be the same. Where it helps is maybe I have something like this. Maybe a better example would be this. I'm making this up on the fly. Let me say I have 1 half, 3 halves, 5 halves, and 7 halves. Can we do multiplication with fractions? Certainly. It's just the same math we've been looking at, right? But I find dealing with the fractions is more challenging, right? I'm more likely to make a mistake. So I might look at this right here and say, wow, that really looks like 1 half times 1, 3, 5, 7. And now I just turn it into this, 1 half of 1, 2, 3, 4. And that leaves behind 1, 3, 5, 7. So then I multiply these together. And then after I've got my final 2 by 2 matrix, I multiply by 1 half. It just can make the math easier at times. Or I may look at something, what if I'd had this? 1, 2, 3, 4. 1 half, 3 halves, 5 halves, 7 halves. And then say over here I had 2, 4, 6, 8. Well, I realize this right here is really this. 1, 2, 3, 4. 1 half times 1, 3, 5, 7. And this I can factor 2 out of everything. Leaving behind 1, 2, 3, 4. Right? Because 2, 4, 6, 8. Well, now I can factor all these scalars out. Here's 1 half times 2. So really, even though they're sort of going to cancel out, that was on purpose, I end up with 1 half times 2 times 1, 2, 3, 4, 1, 3, 5, 7, 1, 2, 3, 4, right? And these, since that's 1, I don't even need to deal with that. Then I use what we saw about associativity, where I can either multiply these two together and then multiply by this, or multiply these two together and then multiply by this, as long as I make sure to stay on the correct sides for what I'm doing. But I can do that. So I cannot stress enough, you have to learn that in general, that is not true. Okay? Now what about vectors? Well, same things apply to what we said earlier, right? If I have something like, we'll see this a lot, we'll have like a times x. Once we start talking about systems of equations, we'll do this all the time. But all this is really saying here is something like this. I might have 1, 2, 3, 4 times, say 5, 6, right? So what are the shapes? 2 by 2, 2 by 1, and so the result will be a 2 by 1. So I'm going to have 1 times 5 plus 2 times 6. So that's 5 and 12 is 17. And 3 times 5 is 15. So 15 and 24. Right? So that's my 2 by 1. This is why I said in an earlier video that how we write vectors matters if we're doing arithmetic with it. If I'd had this, this would not be a legal product, so I would not be able to do this. Okay? So we talked about addition in another video, subtraction in another video. Now we talked about multiplication. Didn't talk about division because it is not defined for matrices. Okay? So you should never have something like this. Capital A divided by B, or 1 divided by A, where these are all matrices or whatever. You should never do that. That's never legal. All right? But matrix multiplication is something we're going to do for the entire course for a variety of reasons. So you have to get on board with how to do it and also know that's legal and not legal. And I will tell you, for many years of teaching linear algebra, there's people still at the end of the semester trying to do this. And I don't know how else to tell you that you can't do that other than what I've said. Okay?